Okay, think about a massive, complex system completely failing. We're talking an entire airline scheduling grid crashing or a spacecraft just losing communication. Now, why does that happen? Well, most of the time, it's because engineers tried to string together a million different processes. They're just patching verbs on top of verbs until the timeline simply breaks. Today, we're decoding a fundamental shift in how we approach systems design to prevent exactly that. We're moving away from the trap of engineering processes and stepping into the exact mathematical precision of engineering properties. Let's dive into an incredibly powerful concept from our source material, known simply as the lever.
So here's our roadmap for this explainer. We're going to hit four main pillars. First up, the engineering trap. Second, defining the lever. Third, the two absolute conditions. And finally, the verification revolution. We've got some incredibly dense but vital engineering concepts to demystify, so let's get right into it.
Section 1. The engineering trap. To really get why we so desperately need this structural shift, we've got to recognize the massive trap engineers fall into when they're told to build complex systems.
Here's the bottom line. You absolutely cannot engineer a property if you're still just describing a process. Our source text points out a huge danger here. If you define a system purely by what it does, using verbs, your engineers are going to build a machine that just does that thing. And that usually leads to massive unintended consequences and just endless complexity. Let me give you an example. If you tell an engineering team, hey, I need a system that transports me from point A to point B, you're giving them a verb. In trying to optimize that verb, they might waste literally years redesigning and accidentally rebuilding the entire road network just to satisfy that process. To escape this trap, you need a noun. If you ask for a car, boom, you get a specific formal object. For high-level systems design, we need that exact formal object, completely stripped of time and stripped of traversal.
Which brings us to Section 2, defining the lever. If we need a noun to escape this trap of endless verbs, what exactly is the structural noun we're looking for? Well, enter the lever.
So, what is this formal object? The source material defines the lever as a bottomless, grain-complete equivalence class. And formally speaking, this is defined as the quotient space R over G. Okay, I know, that sounds super dense. So let's translate that into plain English. An equivalence class basically just means a mathematical grouping of things that share a fundamental property. It means they can be treated as completely identical for your specific engineering purpose. Imagine you're sorting a massive, chaotic pile of objects purely by their exact weight. Within each weight class, the objects are structurally equivalent for what you need, right? The quotient space R over G represents the mathematical space where this perfect structural grouping happens. This is our noun. This is the exact geometric reality that lets us engineer a true structural property, rather than just crossing our fingers and hoping a sequence of events goes right over time.
Section 3. Two absolute conditions. Getting the elegant math down is really only half the battle. For this to actually work in physical reality, the lever is bound by two absolute, unbreakable rules.
The text outlines a strict two-part condition here. Step 1 is the checkable property, and step 2 is the substrate anchor. Now, I really want to stress this. These aren't just, guidelines or best practices. They are absolute physical and mathematical laws. If either one of these fails, the whole system just collapses right back into being a mere process.
All right, first up is the checkable property. The rule here is that the regraining map, which the math refers to as G, has to be an isomorphism at every single magnification. To visualize this, just think of a fractal. It doesn't matter how incredibly deep you zoom in or how far you pull back and zoom out, the fundamental geometric shape remains perfectly, mathematically consistent. That is exactly what an isomorphism achieves here. No matter the scale, the fundamental structural equivalence holds perfectly intact. It's a beautiful thing.
To fully wrap our heads around this, imagine a parent state and a children's state. Because of this fractal-like isomorphism, the parent is perfectly and completely mathematically exhausted by its children. That simply means the parent is completely defined by the sum of its parts. Absolutely nothing is lost in contraction when you zoom out. And on the flip side, there are no independent ghost bits added into the parent state. Ghost bits are basically rogue data, unverified lines of code that somehow just magically sneak in during a computational process. But since we're dealing with a property and not a process, the data integrity remains mathematically absolute across every single level of magnification.
Okay, moving to the second critical law, the substrate anchor. The text lays out this beautifully simple yet profound rule. The refinement tower has no floor. When you're engineering a complex system, you have this refinement tower, right? It's the layers of system complexity.
You go from high-level user interfaces, down through the code, all the way down to the binary. This rule states that the descent through those layers absolutely cannot stop halfway. So let's look at what this infinite descent actually means for our framework.
The absolute game changer here is that this exactness doesn't just magically terminate in some pixelated software simulation. Unlike a video game physics engine that eventually hits a simulated base layer of pixels and just stops, this math descends all the way down, literally. It descends infinitely until it locks directly into the physical substrate. We're talking all the way down to the actual silicon, the actual copper wires of the real physical world. This is what saves us from the illusion of purely digital alignment. By anchoring directly into the physical world, it ensures our engineering property isn't just some mathematical fantasy, it's locked into unshakable physical reality.
Which brings us to Section 4, the verification revolution. When you take these two absolute conditions, the fractal-like checkable property and that unshakable physical anchor, and you combine them, you trigger a complete revolution in how we verify systems.
Because our regraining map is a bottomless isomorphism, we literally have to change our entire perspective on alignment. The source material outlines macro intent, represented as B times B, alongside micro execution, represented as B1 times Bn. Think of macro intent as the big picture, the overarching purpose of a system, and micro execution as the tiny, granular actions of its code. Now, in traditional engineering, these two things are miles apart, usually connected by really messy, unpredictable processes. But under this framework, the text emphasizes they are not two separate points at all. They are the exact identical physical coordinate, just viewed at different levels of magnification.
So, what does this all mean? It means verification requires zero traversal. And zero traversal means you don't have to run a million simulations over time just to see if the system actually works. Since the structure is mathematically identical at every single level, simply observing its geometry is enough. This geometry contains zero verbs masquerading as structure. Actually, the text points out that if you just drop this exact definition into the top of a technical white paper, it instantly filters out anybody who is still trying to solve systems alignment with a convoluted software pipeline. It just cuts right through the noise of traditional software engineering.
And that leaves us with this incredible 5-sentence geometric mic drop from the text. I want you to really let the weight of this phrase sink in. Reach is verify. You don't traverse a lengthy process to verify if a system is aligned, because it is the exact identical physical coordinate at every magnification. The structural reach itself is the verification. That realization right there, that is the core heartbeat of this entire framework.
Now, you might be wondering, why does this matter for the real world right now? Well, the text reveals that this exact framework is currently being prepared for upcoming intellectual property and legal architecture. The source text actually categorizes this under A1 strategy law, which means this isn't just some academic theory being debated in a university classroom somewhere. No, this incredibly precise engineering property is being formalized into concrete intellectual property blueprints right now as we speak.
And as this framework moves into the ultra-competitive world of IP law, the source material poses a really specific, provocative question. What happens if a competitor tries to patent this mathematical equivalence class, but they do it without the bottomless substrate anchor? Like, what happens legally and structurally if someone tries to claim the math, but fundamentally fails to lock it into physical reality? Think about the massive ramifications of that missing anchor. It's a wild thought to leave you with. Thanks so much for joining me for this explainer, and I'll catch you next time.